If it's intra-county, you're playing Liverpool. If it's in inter-county, you're playing a team, you might be playing Canfield. You're playing a team from a different county. So inter, here's how I finally learned this. The interstate goes from one state to another. Oh, does that help? Did you people already know this? You have no problems with this, and I'm the only one who gets... Okay, okay. So if it's inter-county league, you are playing schools from a different county. If it's intra-county league, which we used to have, maybe they don't have that anymore, you're playing teams from in your own county. The interstate highway system goes from Ohio to Indiana to Illinois. It goes from state to state. Inter is between two separate things, okay? Wow, that's way too thick. So inter means you're going between two different things. Think about the interstate. And so when we're talking about intermolecular forces, we're talking about the forces between one molecule and another molecule. So let's draw a molecule just because we can. So we've got an ammonia molecule. It's got the two unshared pairs on the nitrogen, NH3. It's bonded to 3 hydrogens. And when we're looking at intermolecular forces, we're not looking at the forces within that molecule. Instead, we're looking at the forces, and I'm going to, of course, these, you know, I'm drawing this sort of to make a point. Let's do that. We're looking at the forces between one molecule and the next molecule. Those are intermolecular forces. Easiest way to get sort of a quick proxy for how strong the intermolecular forces are is boiling point. The stronger the forces between the molecules, because what are you doing when you boil something? Okay, obviously you heat it up. You undergo a phase change, right? When you boil things, and you know you can boil anything. You can boil steel. You can boil water. You can boil isopropyl alcohol. You name it, you can boil it. When you boil something, what phase are you starting out with? Discuss it at your table amongst your peers there. And so if we are going to boil something, we're starting off with a liquid. And we're going to move it to what phase of matter? Gas. Yeah, a vapor. There's my little fluffy vapor. In order to do that, what is the change that is happening between the molecules? Stand up. You forced my... In order to get those molecules to let go of that strong grip they have on one another and move around more freely by adding heat, we have to break those intermolecular forces. They're not really bonds. They're not chemical bonds like we find inside a molecule. They're different than that. But we're adding enough energy that we get these things vibrating fast enough that they start to slip past one another. And the stronger the bonds between each molecule are, the more energy that takes. So something that has got really strong bonds between the molecules is going to be much more resistant to melting, to boiling. So generally when we look at a substance and we look at its boiling point, the stronger the forces of attraction are, the higher the boiling point is. What does water boil at? Don't you dare give me Fahrenheit. 100 degrees, yes. Very nice, easy decimal system. Freezes at 0, boils at 100. Isn't that easier than remembering 32 and 212? Who the heck made that up? 0 and 100, perfect. Not that I have a beef against Fahrenheit or anything. Though I do. So, what if we took isopropyl alcohol? Darn it, where'd my alcohol go? So we've got isopropyl alcohol, which is a little organic compound, and we've got water. And I could tell you, let's see, isopropyl, prop is 3 carbons, and it's a fish tail. I can never draw this right. Anyway, there's my worst isopropyl alcohol. So there's isopropyl alcohol. It's not a polar compound. We'll talk. Oh, look at that! The alcohol's about to boil. That was fast. Why does the alcohol boil at so much lower a temperature than the water? If you had to make a wild guess based on the conversation we just had. Hey. Let me get thermometers. Thermometers. I mean, these things we would assume should be pretty close to the same temperature. We put them on the heat at the same time. Oh yeah, the alcohol's boiling. Full on boil. The water's starting to bubble, but... this is at... I think isopropyl boils at somewhere like 80 something. Oh. What could possibly go wrong? Said the woman who was not wearing eye protection. That's kind of dumb, huh? That's really dumb. Okay, well, it's at 74. Full rolling boil. Let's turn that off real quick. Full rolling boil. The water hasn't even started. They look the same. Can't tell the difference to look at them from a distance. The forces of attraction between each molecule in that alcohol and between each molecule in that water are much lower. It has significantly lower intermolecular forces. Therefore, it's going to boil at a much lower temperature. Huh. Now, if we looked at, you should totally have a periodic table out. Basic tool of the trade. So if we took this salt and I fixed up a third beaker and I poured salt in it and I heated, oh, the water's finally boiling, and I heated the bejabbers out of it. Could I boil it? You attempted to melt this stuff. No. You can't even melt it at temperatures with a candle. How are you going to boil it? To boil it, you got to melt it first. You got to make it a liquid. Because we said that boiling is the transition from a liquid to a vapor. Huh. Molecular compounds. Ionic compound. Well, it turns out that intermolecular forces are generally weaker than the forces between ions. These things that are liquids at room temp very often are molecular compounds. Who here has seen vegetable oil? Once again, I will assign homework. Don't make me do it. Go to Aldi's. Vegetable oil, molecular compound, liquid at room temperature. Can you boil it? Yeah, you can. Anybody here doing time at a fast food establishment? I did time at a fast food establishment in high school. It was horrible. And they tend to stick newbies on the fries. And you hang out over grease for 7 hours with a 20-minute break in the middle. And that grease gets really, really hot. When you put stuff in it, it bubbles. Is the grease boiling? Mildly, yeah. It's right at the point where it's going to start to vaporize a little bit, which is why you come home with a thick layer of grease on you from the grease vapor that's come up off the fry pits and coated your entire body. Ugh, delightful. Yeah, are you currently experiencing this? You're laughing like somebody who's done 7 hours on a fry pit. It's miserable. It's horrible. It's awful. The forces between molecules are generally weaker than the forces inside the molecule. So let me pull my ammonia up here. It doesn't take all that much energy to get these guys to move apart, to liquefy, or to vaporize. That's not that hard. You can vaporize that pretty easily. It takes a lot more energy to bust that molecule. The forces inside the molecule are stronger than the forces between the molecules. And has anybody here ever melted any form of metal? Intentionally or not? No? You have. On purpose or not? On purpose. Do you have a little foundry forge thing at home?
I just got bored one day.
A lot of good science starts from, well, I wonder what would happen if. Did you melt metal on purpose or accidentally? Okay. Were you forging things, or were you also just bored?
I was just bored.
Okay. Lots of just bored science out there. I had a student one year whose hobby was melting things. He was an interesting guy. It was a complete pain in my tuchus. He was really smart. He thought outside the box, and he never stopped thinking, which was why he was a pain in my tuchus, because he would come in on Monday mornings and be like, so, I thought about this over the weekend, and this, and then I did this, and then I melted. Here, look, here's a video of something. Okay, yes, you did. Like the kid asked for blowtorches for Christmas with MAP gas. He liked to melt stuff, and he liked to compare melting things. Born engineer, fantastic. Melting a metal, if I crumpled up aluminum foil and put it in yet another beaker and put it on this burner, could I boil the aluminum foil? What would I have to do first? I'd have to melt it first. I'd have to turn it into a liquid. And then from that liquid, can you boil a metal? Sure. Absolutely. On the sun, things like iron and aluminum are vapors. It's that darn hot. But in general, the forces between molecules tend to be weaker than the forces inside molecules, the forces between ions, or the forces in a metal. And we can look at those boiling points and those melting points, and we go, oh, well, yeah, of course. It takes less energy to overcome those forces of attraction. Now, here's where we've got the interesting little weird cases. Polarity. So we talked about this already when we talked about what kind of bonds. So we talked about polar covalent bonds. And the sort of textbook answer for what's a polar covalent bond. It's a bond that forms, creating a region of partial charge on each end of the molecule. Blah, 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 whatever that means. What it means is you've got more electrons on one end. You've got more protons on the other end. And what that creates is a dipole. Di means how many? 2 fingers. Di and bi both refer to 2. A dipole is something that has 2 poles. Much like, hey, Matthew, can you hold up your prop? Oh, you brought the new one. Cool, I want to see this later. Okay, those are little tiny magnets. Magnets have a dipole in them. They have areas of unequal charge. Unequal charges are attracted and repelled. Attracted. Unequal charges are attracted. The North Pole and the South Pole of the magnet are attracted to one another. We call them North and South because those are words we made up, and we superimpose this whole sort of framework on everything, which is fine. That's, we're humans. That's what we do. So we get these little dipoles between molecules that have areas of charge on each end. Let me draw my favorite. So I just drew the water molecule, and you've built the water molecule and drawn the Lewis structure for it. So you know that you've got an oxygen in the center, you've got hydrogens attached to the oxygen, and then you have those unshared electron pairs. So you got 2 things going on here. Number 1, you got unshared pairs. So that right there creates a region of sort of an uneven charge. But furthermore, which is more electronegative, hydrogen or oxygen? Look at your periodic table. Electronegativity tends to increase towards the halogens. Which one is more electronegative? You can hold up sign language for this. This is H, this is O, H, O, H, O. Which is more electronegative? Oh, yeah. Oxygen's pretty darn electronegative. It tends to be a bit of a blanket hog when it comes to electrons. So it not only has those unshared pairs, but it's also sort of pulling some of the electron cloud off the hydrogens. Well, what that means is you have a region of And they always show this with this little symbol, which I can never do a good job drawing. It designates a region of partial charge. Don't even try it. I usually just put pluses and minuses. If you are somebody who is going on in chemistry, you'll see this little designation. It looks like some kind of weird, messed up D, and it means it's a region of partial charge. And then you have a region of, same symbol, negative charge down here. Well, we know that water is a polar compound. Water's got these regions of partial charge. What that means is that when we have an entire big beaker full of water, all of these little dipoles sort of line up. And you get forces of attraction between the positive and negative ends of adjacent molecules. What does that do? What do you think that does to the boiling point of the substance? Talk amongst yourselves. You all got that. So when you've got polar substances, when you have some degree of molecular polarity, what you see is a higher boiling point than you would expect otherwise. So molecular compounds like that alcohol, yeah, it's fairly stupid. Picking up glassware with bare hands, no eye protection, what could possibly go wrong? That alcohol is a molecular substance. That water is a molecular substance. Why does the alcohol boil at so much lower a point than the water? Oh, look at that. Here's our alcohol. Our isopropyl alcohol doesn't have any polarization. It's a nonpolar molecule. There are no dipoles. There are no little forces of attraction between the molecules. In the water, we have forces of attraction between the molecules. Now, water is interesting because not only do we have a dipole with water, we have one other thing. Water has hydrogen bonding. Oh. So hydrogen bonding specifically involves hydrogen atoms. I know, who would have thought? That's so crazy. That was sarcasm, by the way, just in case. When you've got a hydrogen atom, especially if it's bonded to a highly electronegative atom, something that's going to pull the electrons off of it, and you've got unshared pairs of electrons nearby. Does this sound like anything that you've just seen? Let's see. So water has not only, polarity, but you've also got those hydrogens with the blankets being pulled off them with a fairly significant positive charge that are actually attracted. Now, I'll choose one more color to do this. Let's get be a good color for attraction. Purple. So not only are those hydrogens attracted to the region of partial charge, they're actually strongly attracted to the unshared pairs. So it's not only a polar molecule, which raises its boiling point. It's got hydrogen bonding, which raises its boiling point. Also creates surface tension. Who here has seen a water strider? Little tiny bugs, they walk on water. Cute. Yeah, little discs on their feet. They're walking on water tension, on surface tension. And that's the fact that there's this sort of skin that forms on water. It's due to the hydrogen bonding, because those hydrogens are very attracted to the unshared pairs. London dispersion forces. I don't know why they're called London. I don't know why they're called dispersion, because they are, by definition, attractive forces. This makes the least sense to me of anything. If anybody wants to email a real chemist and ask them that, please feel free. I used to have a physicist I email her occasionally with stuff like, hey, Dr. Krishimano, why is this? So London dispersion forces are super weak. They exist in all substances, including noble gases, which is sort of this gas. Because, you know, the thing that we think of, like noble gases have no forces of attraction to any other molecules. They're completely aloof. They don't bond. They don't participate in exchanges of any sort. you do see little bits of London dispersion force even in noble gases. And what happens, so remember that those electrons are moving around. Let's draw our, so we've got the tiny dense positive center, and then we have the giant cotton candy fuzz of electrons that are constantly in motion. We never know where they're going to be. It's very random. It's very rapid. Can it end up that at some points, just by chance, all the electrons are on one side of the electron cloud? Yeah, that can happen. What you get is this sort of momentary dipole. You get this tiny second of time where a nonpolar substance has a pole, whoop, flashes into existence, flashes back out of existence. And what that does is it creates these London dispersion forces. And it's just like a glimmer of attraction, and then it's over. Done. Boom, done, boom, done, boom, done. So they're the least important of the intermolecular forces, but you should be at least somewhat aware of them. They're not terrifically important, but they do happen. They're known and described. That's it for this chapter. So after the bell rings, we'll grade homework. And then tomorrow, which might be Monday, is your test. Do you think there'll be Lewis structures on your test? If anybody needs help with Lewis structures, if you need additional tutoring, I'm here till 3:15 every single night. I have fourth period planning. So, does anybody have any questions on Lewis structures based on finishing up the lab?